Evening, everyone. Welcome to today's webinar. My name is Xuemei You from Editorial Office of Journals Theoretical and Applied Mechanics Letters. It's my honor to start this webinar. Before we delve into today's stimulating discussions, please allow me a moment to introduce both our journal and today's webinar. TAML aims to publish cutting-edge research in theoretical, computational, and experimental mechanics, emphasizing originality and rapid dissemination of advances in science, engineering, and technology. The impact factor for this year stands at 3.2, with a CITE score of 6.2, reflecting the high quality and relevance of our published research. We ensure swift publication with an average time to first decision of just 3 weeks, facilitating timely exposure of groundbreaking work to the academic community. TAML is led by Editors-in-Chief Professor Guo Weihe and Professor Yonggang Huang. Our dedicated team consists of 75 editors and board members from 17 countries, all affiliated with prestigious universities and research institutions. This diverse expertise ensures the TAML maintains the highest standards of academic excellence and integrity. We are committed to providing exceptional support to our reviewers, authors, and broad community, guiding you through every step of the publish process with our extensive expertise. We warmly invite you to consider submitting your research to TAML and join our growing community of contributions. Let's move on to the next slide to introduce the specifics of today's webinar. Thanks. This webinar is jointly hosted by TAML, Elsevier, and Chinese Society of Theoretical and Applied Mechanics, at the National Nature Science Foundation or China Basic Science Central Program, focusing on multi-skill programs in nonlinear mechanics. Our goal is to offer an international platform for researchers to communicate and share their latest work, fostering collaboration and advances knowledge in our field. You can follow the webinars through our webpage on Elsevier and CSTM, join our WeChat group via the provided barcode, or follow us through our other communications channels for continuous updates. Finally, I would like to extend my heartfelt gratitude to everyone involved in making this webinar possible. Special thanks go to today's speaker, Professor Serhii Yarosovich, and today's webinar host, Dr. Qingqing Ye. Your contributions are invaluable to the success of this event. Thank you for your attention, and I look forward to an engaging and informative webinar. Now, I would like to pass the baton to our webinar host, Dr. Qingqing Ye, who will take us through the next section of our webinar. Professor Ye, over to you.
Thank you, Xuemei. We are really happy, Serhii, we are really happy to have you here in our webinar in TAML. And before we start, I would like to make a short introduction about you and the talk. Dr. Serhii Yarosovich is a full professor in the Department of Mechanical and Microtronics Engineering at the University of Waterloo, Canada. And he is also the director of Fluid Mechanics Research Lab. And among a lot of his research area, he's more involved in the experimental research using particle image velocimetry and also advanced measurement techniques to study the effect of operating of lifting surface and low Reynolds number, bluff bodies, flow separation, and flow control especially. And he is the Alexander von Humboldt Fellow, a Mercator Fellow, and also the Associate Fellow of AIAA. And he is also serving as Editor-in-Chief of Experimental Thermal and Flow Science. And today he's going to talk about he's going to talk about the airfoils and wings in aerodynamically low Reynolds number flows. Okay, Serhii, the floor is yours.
Thank you kindly, Ching Ching. Okay, can you see my screen?
Yes, it's clear.
All right. Thank you, everybody, for joining. Most of you would be in a very late hour, so this is much appreciated. It is my privilege to share some of the results of our work with you. And without further ado, I'm going to jump into this discussion here. So our outline of the talk is going to be as follows. We're going to introduce you to low Reynolds number aerodynamics domain and talk about what are the common flow features thereof. Then we talk about flow stability and transition, the dynamics of these phenomena in three-dimensional sense. Then move on to the finite wings from two-dimensional nominally airfoil geometries and talk about some unsteady phenomena involved, concluding with the summary at the end. So low Reynolds number domain, of course, is aerodynamically relevant. So when I share with my colleagues that we do low Reynolds number aerodynamics, of course, people in fluid mechanics would think of Reynolds numbers and creeping flow, but for aerodynamic flows, these are quite high chord-based Reynolds numbers. So this is a representation of some of the applications in the domain where I'm plotting chord Reynolds number here on the horizontal axis. And vertical axis here is the velocity at which the particular system operates. And when we're talking about low Reynolds number dynamics, we're referring to Reynolds numbers below approximately 500,000. And you see there's a number of applications that are involved in this domain, from biological applications such as insects and birds to man-made systems, wind turbines, drones, unmanned aerial vehicles, etc. So what happens is aerodynamics is quite different here from classical aerodynamics and warrants special attention for the prediction of flow development as well as the performance of the systems. In particular, what happens at low Reynolds number on the suction side is that the flow, when exposed to the adverse pressure gradient, is illustrated here. So when you're entering the adverse pressure gradient region, flow eventually separates due to a relatively low momentum that possesses, and the separated shear layer can undergo transition, being much more unstable than the attached boundary layer, and the enhancement of momentum exchange can lead to time average flow separation, as shown here by the gray out region. And this topology in the flow is referred to as laminar separation bubble, or if the phenomenon is quite dynamic. So I'm going to superpose on this cartoon here an actual video of laminar separation bubble that is visualized using a smoke injection into the separated shear layer, and you will see that the phenomenon is quite dynamic. You see here in a separated region, flow being fairly laminar, and the undulations are starting to develop, leading to the formation of periodic shedding of vortical structures. And you can see quite rich dynamics of these structures. Some of them merge, but all of them start to break down close to the time average reattachment point. This phenomenon has been investigated since the 60s of the last century, and adverse effects associated with this include performance degradation of the airfoil, abrupt stall, unsteady loading, and noise production. And this is why it's quite important to be able to predict and understand this process on the suction side of the wing. So the transition to turbulence plays a key role because, in fact, it actually determines whether or not the flow reattaches, so the airfoil stalls past separation, and then stability considerations become quite important. It's our next stop here. In the discussion, I would like to highlight that we will primarily focus on some of the results produced by our group here. And however, there's plenty of other research findings and many excellent papers on the topic. So I'll use our results nonetheless to provide a holistic summary of the state of the art in this area. So here's the flow visualization quantitatively using span-wise vorticity. I'm plotting it here in a wall-attached coordinate, where y is the wall normal and x is the attached surface tangent coordinate. And what you see is the shedding of these structures in the separated shear layer and their breakup in the aft portion of the laminar separation bubble. And looking at the statistics, the classical mean velocity is recovered here, where the solid black line is showing the separation streamline that divides, roughly outlines rather, a laminar separation bubble region. So you can see then using the streamline, we can identify separation location, reattachment location, and maximum height marked here. And the other two images are showing root mean square fluctuating velocity components, the wall tangent and wall normal, respectively. And you can see along the separated shear layer marked by the displacement thickness here in the dashed line, you see amplification of disturbances that takes place quite rapidly and peaks around the reattachment region here. And similar with the wall normal components, we see a similar story. So in the frequency domain, so doing the spectral analysis of these fluctuations, I can plot the Struhel number, which is a non-dimensionalist frequency, in this case using the chord as free stream velocity for normalization. And this is the streamwise distance along the surface. We can identify that perturbations start to get amplified here within the band of certain frequencies here. And eventually, the amplification band broadens quite significantly, marking later stages of transition where perturbations start to break down to multiple scales. And finally, we start seeing spectra similar to the turbulent flow spectrum. Looking at the stability predictions of this flow, we can do linear stability analysis on the mean velocities measured in the experiment. And here is the sample of a wall normal velocity fluctuation spectrum in black, and overlaying on it the n factor coming from the linear stability analysis. And you can see that we can reasonably well predict the frequency of the most amplified perturbation. So in dimensional sense here, for this particular case, that's around 125 hertz or so. So linear stability theory works quite well in predicting the original amplification of perturbations and their characteristics for these flows, despite slight non-parallel effects and later on nonlinear effects present in the flow. So further on the stability consideration, we embarked on a campaign to actually look at how controlled perturbations would develop in this flow. And for this purpose, we performed experiments on a flat plate subjected to artificially induced adverse pressure gradient using the top flexible wall here in the facility. And we're measuring in this domain where the laminar separation bubble forms. And we're using a plasma actuator located upstream of separation in order to introduce controlled perturbations of a given frequency and amplitude. So here are surface pressure distributions that are shown in blue. This is distribution that we obtained by tripping the flow, so eliminating the laminar separation bubble. And in black is with the laminar separation bubble. And you see the characteristic pressure plateau and pressure recovery due to the presence of flow separation, marked by S as a separation and R as the reattachment here. So measuring the velocities, what we do is we use particle image velocimetry in this experiment, and the black points here show the actual measurements in the laminar portion of the flow. And what we wanted to do is we wanted to trace the development of perturbations upstream. So in the region outside of field of view, where it is extremely difficult to actually measure minute perturbations in the flow due to the signal to noise limitation of any instrumentation. So instead, what we decided to do is to investigate the full spectrum using numerical modeling for the attached upstream flow and multi-separated flow using boundary layer solver upstream. with the input being the surface pressure distribution that we measure experimentally. And this result shows you the comparison of the measurements and in the blue line boundary layer solver results. And as you can see, we're very well matching the experiments. What that allows us to do is to do a compound stability analysis of the flow using upstream the numerical model results and downstream the experimental results. And so this is the outcome of the stability analysis. This is the non-dimensional frequency as a true whole number. X is plotted here as a streamwise coordinate normalized by displacement thickness at separation. And the contour lines are showing the contours of the growth rates. So dashed line connects the local maximum, the growth rate, so showing the local frequency associated with the maximum growth rate. And what you can see on the left of this vertical demarcation black line, I'm plotting the results from the solver, while on the right, we're plotting the results obtained from the particle image velocimetry. And you can see these contour lines matching very well. So what it tells us is, not surprisingly, that the stability characteristics of both the attached flow and the separated flow are described by a continuous spectrum. So there is a continuous transformation from the attached flow transition, with the critical point being reached upstream of separation. Separation is located here, so critical point is reached here. And the perturbations are developing via a continuous spectrum. So there is no fundamental separation between the Tollming-Schlichting waves dominated transition that is happening upstream versus Kelvin-Helmholtz type of instability dominating in the separated flow. The former ones are forming, developing, and feeding into the latter, and they both form a continuous spectrum. So that's the way the transition progresses in this particular scenario. Further on stability considerations, we can use controlled perturbations in order to see how the controlled perturbations can be used to influence the flow development, but also gain further insight into some of the stability characteristics. And here I'm showing the results of the actuation on the laminar separation bubble. So the mean velocity profiles in a streamwise direction are shown. There's no actuation at the top, continuous plasma actuation. And here we're modulating the plasma actuator at the different frequencies in the hydrodynamically relevant range. And you can see that the selection of the frequency while maintaining the amplitude input constant has a significant effect, with the minimum bubble achieved at the F plus of approximately 6 in this case. And this can be explained quite well from stability considerations of the flow. So here at the top, I'm plotting the velocity profiles on which the stability analysis is done in solid lines. And I'm comparing these profiles to both the attached laminar boundary layer, so fitted here as the dashed line, and this dotted line as the unbound free shear layer using the hyperbolic tangent profile. So this plot at the bottom here shows the variation of the normalized growth rate on the vertical axis versus normalized frequency on the horizontal axis. And what you see is, as our shape factor here, denoted as H, increases from 1, 2, 3, 4, so from about 4 to about 6, we see a strong increase in the growth rates here in the transition process. For comparison, this would be your stability characteristics of attached boundary layer, and you can see very dramatic increase in the growth rates, which explains why the transition happens so quickly in the laminar separation region over here. But in comparison to the free shear layer, of course, our growth rates are still notably lower, which highlights the dampening effect of the presence of the wall here. So with the stability characteristics highlighted, I'd like to move on and illustrate how the three-dimensional dynamics of the laminar separation bubble looks like and what's involved. So with the instabilities amplified from the attached boundary layer and entering the separated shear layer in the continuous spectrum, as they grow, they eventually
So here, I think we lost you for.
Yeah, sorry, I'm back. Is that okay? Can you see the screen?
Yeah, now it's back.
Oh, yeah, I'm apologizing. Something must have happened over thousands of kilometers of the internet connection.
Okay.
All right, thank you so much, and apologize for this interruption. It doesn't seem to be any problem on the connection end, so I'm not quite sure. We blame Microsoft. Okay, so apologies. So what we're seeing here is the relatively spanwise uniform roll-up of these structures, but you can see them undergoing quite significant deformation very early on, and this is nominally two-dimensional geometry with end plates. So we're seeing this on 2D wings. So there's quite significant 3D flow development, and what you can see here is the PIV based visualization of the same, and you see the spanwise uniform structures undergoing quite significant deformation and eventually break up. So similar results were obtained by others, and depending on the particular facility, you can see more significant deformation, such as these ones done in the water tunnel by Bergman and Schroeder, with relatively high free stream turbulence intensity, or these done at TU Delft by Nadia and colleagues, where you see more uniform formation of these structures and eventual breakdown using tomographic PIV. So we've embarked on investigating this three-dimensional dynamics using tomographic time-resolved particle image velocimetry. The setup is shown here. The experiments were performed on a similar geometry on a flat plate here, as discussed earlier, and the tomographic PIV was restricted to these region at the aft portion where these vortices are forming. So there's a Q criterion highlighted structures with colors indicating the strengths of spanwise vorticity. I'm going to play that as a video here. What you see is strongly deformed structures breaking up in the aft portion of the laminar separation bubble. And what we wanted to do is we wanted to understand where these deformations are coming from. There's quite significant debate in the literature, or at least it was at that time, of the nature of instabilities that are causing the breakup to turbulence. So when we're analyzing these structures, what was peculiar, so these are histograms, and we see prevalent streamwise wavelengths of these structures centered at this mean value here. But we also see prevalent spanwise wavelengths to these structures, which is about 2.5 times the streamwise wavelengths in this case. So that hinted that there is some fundamental instability that may be in play in this flow that results in the connection between the breakup and the characteristics of the structures themselves. So looking more into details in the stability analysis here, I'm plotting the growth rate versus streamwise distance, and I'm looking at the normal mode, so shown in solid line, and the first oblique mode showed of perturbations shown in dashed lines. So through the stability analysis, the long and the short of it was that, as expected, our normal mode transition is dominating. So we see the more negative growth rates, which means that these perturbations are more amplified than oblique perturbations. However, our oblique waves that are present in the flow are also amplified, and amplifications are not trivial, and you can see this from the N factors here. So they're amplified less. So at any given streamwise distance, we have a lower N factor for the oblique mode than for the normal mode. However, they are not dampened, or not all of them are dampened, and oblique modes of specific characteristics and oblique angles are amplified in nominally two-dimensional flow. So using a simple cartoon, what we can illustrate is if you go with superposition of normal mode and a pair of oblique modes, because those do come in pairs, what you can have is the deformed wave fronts, right? And the degree of deformation of these wave fronts will depend on the relative magnitude between the two modes. So in this case, the relative magnitude is in favor of stronger oblique modes, whereas in this case, it's weaker oblique modes in comparison to the normal mode. So in order to verify this, although the results were obtained on the experimental data, we wanted to confirm that we can actually control these deformation by changing the amplitude of either oblique or normal mode. In our experiment, it was easier to control the normal mode. So what we've done is we used a plasma actuator that is spanwise uniform and located upstream of the separation to introduce a controlled spanwise uniform normal mode and see how that would affect the transition process. And how, based on the numerical and analytical calculations, with the stronger normal mode, we would expect to see less significant spanwise deformations. And on the left, what you see is the natural transition video for comparison, the one that I showed you already, highlighting the structures that we're seeing in the laminar separation bubble. And on the right, you see the forced one. And as you can clearly observe here, as we're forcing the natural normal mode, what happens is we get a much stronger spanwise uniform structures that with the spanwise deformation suppressed, supporting the analytical conjecture made there that the superposition of the two modes and their relative magnitude may play a role in determining the initial deformations of these structures. We can also do this the other way. So instead of forcing the normal mode, we can introduce an oblique deformation and see how that would develop. And for that purpose, we performed the following experiment using the two actuators upstream of the laminar separation. The first actuator here was 2D uniform as before, whereas the second actuator was segmented in the spanwise direction to introduce the perturbations with a fixed wavelengths. And on the left, you see natural transition PIV from the top view, cutting through the tops of the rollers, so they appear as dark bands. So you see these structures forming and undergoing deformation, very similar to the experiments that I showed you with tomographic measurements. And here we're introducing two-dimensional disturbances, and as before, we can regularize the shedding and reduce the spanwise deformations observed in a natural flow. And what we also can do is we can induce controlled spanwise deformation. So here at the 2.5 wavelengths of streamwise vortices, and you can see that we can, in a controllable manner, introduce these deformations here. And what the results showed that these deformations are amplified, are naturally growing in the flow, confirming our conjectures further regarding the nature of these three-dimensional dynamics that we observe. However, there are also other conjectures in the literature. In fairness, they need to be acknowledged. There's suggestions that these may be attributed to local elliptic instabilities in the braids. They can be Gertley-induced instability and some other results. What I would like to propose here is it doesn't, at the end, perhaps it doesn't really matter what the initial perturbation origin is. We've constructed a small model or a relatively simple model to illustrate that as soon as these perturbations appear, they will be amplified naturally in the flow. And in order to convince you of this, I would like to produce the results here. So what we're doing is a model which combines the mean flow convection, so basically taking a mean flow measurements and imposing the mean share in the flow, as shown here. Inducing Biot-Savart, so we're introducing a vortex filament in the flow, as shown by blue, and we're adding its mirror image counterpart to model the wall, modeling Biot-Savart induction. And the wall effect, of course, is introduced here. So combining these, we're introducing a filament with minor undulations shown here in the imposed flow. And what I'm showing you how this will develop using a simple analytical simulation here. So the structure will advect as I play the video, and on these two images, I'm showing how it's the top view, basically a plan view of these structures, and here a front view looking upstream, seeing how these deformations develop. And what you see that these deformations will naturally amplify due to self-induction of the structure and shear effects. And what you also see here, that these structures will start developing wool normal deformations as well, similar to hairpin structures with the tips lifting away from the surface. So regardless of the nature of the initial deformation, the moment these structures have any spanwise undulations, these will deform naturally in the flow that these structures are exposed to. Which will lead to deformations and eventually vortex breakdown. So the majority of these studies in prior literature, including our own work, has been done on two-dimensional airfoils. And you can see that these structures and the flow development is strongly three-dimensional and unsteady and quite complex, even on two-dimensional geometries. But in reality, of course, all of the our applications involve some finite geometry effects, such as wing tip and wing root effects, or blade tip, blade root effects. And it's important to understand how the low Reynolds aerodynamics flow development takes place on practically relevant geometries. So with that, we embarked on looking at the finite wing geometries. So this is just planar wing on an NACA 18 profile, and we're looking at first tip effects, and then we'll look consequently at the root effect. So here we're doing measurements using stereoscopic PIV at different planes, moving towards the tip, and you're seeing flow development very similar to the bubble on airfoil geometry. These are streamwise velocity profiles here shown at different spanwise locations identified by the planes shown here. And I'm going to be moving towards the tip, and as I start moving closer towards the tip, you will see significant changes in the flow. So our separated flow region diminishes and eventually vanishes at this point as I go closer and closer to the tip. So at this location, I don't see the blue regions that would be indicative of reverse flow, so the separation seemed to be suppressed. And as I look at the mean spanwise velocity, as expected, I'm going to see a strong tip vortex here, and with the pressure at the tip being here lower, I'm expecting the inward flow here into the, or higher, excuse me, expecting to see the inward flow towards the wing root, and that's exactly what I'm observing. So I'm observing flow in the negative Z direction, so negative flow towards the root. But what's interesting is that magnitude of that flow is concentrated with the location of the laminar separation bubble. So there's a very intricate interplay between the three-dimensional flow development and the local separated flow region development. So reconstructing this geometry using multiple measurements, I can construct the separated plane in this case, so surface marked by red. So rather than the separating streamline, that would be a separating surface. And you can see that the topology of the laminar separation bubble on the finite wing will be an open separation with the flow going in to the separation bubble as shown here. And mind you, these are not cartoon sketches. These are actual mean flow reconstructions based on finely spaced stereoscopic flow measurements. So looking at the dynamics and changes in vortex dynamics of the wing, these are phased average results using proper orthogonal decomposition. I can elaborate later on if anyone is interested, but the details are in this reference in the paper if you would like to get more details on how this is done. And so these are phased average results shown here. The dashed line shows roughly location of time average reattachment. And you can see that very similar to the 2D geometry, we see the shedding of the shear layer rollers. However, as I approach the tip, the dynamics of these structures changes, and eventually I can't identify them no longer. So the wing extends up to this location. Nonetheless, within the core of the fault low, away from the tip, I seem to recover a relatively two-dimensional like flow development despite the wingtip presence. So looking at the particular planes here, so starting from plane at Z on C of 1 to 5, I recover in the planar measurements this classical formation and shedding of the shear layer vortices. And as I approach the tip, I still see this at Z on C of 2. However, closer to the tip, the dynamics will start to change quite significantly. So our roll-up location is moving downstream. And eventually, very close to the tip, I don't see any evidence of the shedding in the results. Moving on to the wing root, sufficiently away from the junction flow, I see the topology very similar to laminar separation bubble. And moving closer, first, I don't see any notable changes. However, closer to the root, changes will start to get more clear. So similar to the tip region, we get a reduction in the size of the separated flow region marked in dark blue here. And eventually it is almost suppressed. Here I cannot get any closer to the wall due to reflections, but obviously as we have incoming boundary layer, in this case it's turbulent boundary layer on the wind tunnel wall, we will suppress this region due to the influence of these turbulent nature of the flow and the junction flow development. Similarly, I'm using stereoscopic PIV, so I can look at the out-of-plane motion here, and here I will have the flow towards the tip from the root, so positive spanwise velocities. And again, these are quite closely aligned. The peaks of this spanwise flow is closely aligned with the location of the separated flow region. So stitching together the wing root and wingtip regions, I can get the overall view of the structure. So here are these this separation surface identified with and is colored by the wall normal distance. And you can see that it's an open separation on both ends. So I say I have an inflow here and an inflow at the tip. And although the height varies quite a bit, but it remains reasonably two-dimensional in the core, it gets thicker towards the tip and towards the root region before opening up to the flow. Looking at the dynamics in both regions, I am recovering reasonably two-dimensional flow dynamics here, and the changes are confined to the regions close to the root and the tip here. What's interesting to us here is that as any senior student in aerodynamics would tell us that we are expecting to see a change in the effective angle of attack here. And of course, that change in the effective angle of attack from root to tip should change the characteristics of the flow. And it does. However, it doesn't seem to be changing significantly the dynamics. So the characteristics of these structures seem to be locked onto the instability mode dictated by the angle of attack at the root region. So the laminar separation bubble dynamics does not seem to be responding to the effective angle of attack changes across the span and the finite geometries here. We move on to the transient effects in my talk related to LSB bursting and reformation. So specifically what happens very often and what the danger of these types of flow is that these laminar separation bubbles can burst or suddenly change in size. And that happens when either Reynolds number or angle of attack change and cause the bursting process. So for example, angle of attack increasing or the Reynolds number decreasing. It also can change in response to the perturbations in the incoming stream. And this is a very dangerous process, particularly for gliders, as it causes a sudden stall and loss of control for the pilot. So here we wanted to see how these bursting and reformation of the bubble take place, and primarily what are the time scales as well as the physical mechanisms involved in order to gain insight into these unsteady processes that we haven't had a chance to explore in the past. And the results I'm going to show you initially involve the changes in the bubble dynamics due to changes in incoming free stream. So here we can be decreasing the free stream in the wind tunnel facility as shown by the red line, or increasing it using the blue line here. So first, this is we're going to focus on what the instantaneous flow field looks like for the limiting case. So this is the higher Reynolds number where we should have a laminar separation bubble. So this is the plan view of the measurements, and we're cutting through the laminar separation bubble. It's a little bit thicker at the middle of the wing here, as seen on this image. And I'm seeing the corner separation here due to the junction flow. I am taking these images with 3 cameras here, and a laser sheet is cutting through. And this is sort of a cartoonish sketch of how the laminar separated flow region looks like here on the surface. And I'm cutting through this thicker portion, which is reflected in the measurement that I'm displaying here. So the other limiting case is the fully stalled case, and the corresponding image is shown here. So you see negative velocities here across the span in this instantaneous image. And so this is indicative of the flow separating close to the leading edge and remaining separated until the trailing edge of the wing. So dynamically, let's have a look what happens when I'm actually decreasing the Reynolds number first. So the video on the left will be showing how the flow field responds to the decrease in the Reynolds number. Video on the right will show how the Reynolds number and the lift coefficient in magenta change. So you see bubble bursting, and you see bubble bursting initiating from the middle plane, so where the bubble is the thickest. Now this would be, of course, subjective to a particular geometry and conditions. So it would start at the thickest separated flow region, and it moves outwards, eventually spanning almost the entire wing, with the exception of the tip region where wingtip effects cause local suppression of flow separation. These are, of course, associated with a dramatic change in the lift, so drop in lift, and notable fluctuations in the lift due to the associated shedding of larger scale structures in this flow. Okay, the opposite reformation can be induced as the Reynolds number is increased instead. And here I'm showing the video of a response of the flow to increasing the Reynolds number here, and associated change in the lift coefficient is shown in this pink magenta color. So the reattachment process here is seen to progress in the reversed order and is associated with the flow reattaching first closer to the tip and the root region, and then the separated flow region shrinking to the quasi-steady laminar separation bubble development is seen for this Reynolds number. In order to evaluate how long it takes, roughly, what I'm doing is I'm averaging the flow at a given X location. So taking rather at any Z location and averaging the flow values all around. So I'm going to be able to see at each Z location what are the averaged velocity values here, marked by tilde. And when I have the separated flow, these average values, of course, will be lower. When I have attached flow, these average values will be higher. So for bursting, I would be starting with this picture here, where I have slightly thicker bubble here, so slightly lower velocities in the middle. and this is the time axis in convective times. So we'll be able to see roughly how this flow development progresses with time. And as we saw in the video, it opens up and then reaches quasi-steady state conditions. So roughly, I know I started to see changes here, and it gotten to about within 1 standard deviation of the fluctuations here. So it's roughly 40 convective time units that it takes. And for reattachment process, a similar analysis can be done to evaluate the time scales associated with reformation of the bubble. And that also will be around 40 convective time units. What's interesting that if I compare this to the 2D airfoil, and we've done the experiments for comparison, the bursting and reattachment process seem to be happening much quicker and about twice as promptly as on the wings. So attributed to the lack of the root and tip effects, of course, in this geometry. We've also done experiments with changing the angle of attack. This is a busy slide, but I'll walk you through this. What's most important here is to focus on the effect of the, on this axis, the rate of change of the angle of attack, normalized appropriately. And this is the delta D step is the time it takes in convective time units for flow to reattach or stall. Multiple configurations, airfoil, stall, airfoil reattachment, wing stall, wing reattachment. What's interesting is that as I increase my rate of change of the angle of attack, I'm able to decrease the response times, and I'm reaching saturation limits here at around 10 convective time units. And these are comparable to Reynolds number changes. So the ones that I showed you were these characteristics, so around 40 and 20, but at a lower angles of attack, I can get slightly lower delay times. But overall, what's important here is no matter how the bursting is induced, either to the change of the angle of attack or the change in the free stream velocity and in your operating system, it takes on the order of 10 convective time units for the process to be done, which has important bearings and important consequences for flow control characteristics and the aircraft control characteristics in particular. And finally, to close off, what I wanted to show you, there are recent results that are illustrating how this laminar separation bubble forms to begin with. And these experiments are done in the towing tank facility, starting from rest to mimic the startup of a system. And what I'm showing you here is how the free stream velocity changes in this plot versus how the flow over the airfoil, in this case is an SD profile, changes with time. So there are two fields of view shown here, and these are not time correlated, so they're done in different experiments. So what you're seeing is the flow accelerating, boundary layer development on the bottom side, and suddenly we see the appearance of perturbations in the entire field of view, and these perturbations develop as time progresses. These are streamwise velocity results at the top. I'm going to play that video using spanwise vorticity. And here, what I would like you to notice is that the development of these perturbations seem to happen almost instantaneously across a finite region. And it happens only when the airfoil is finished accelerating to steady state flow. And takes quite a long time in convective time units, so distance traveled over chord here, for the flow to settle on quasi-steady state development of a laminar separation bubble, very similar to the one that we've observed before. So the characteristics of this flow development, without diving into too much details, are indicative of an absolute instability, similar to what's observed at the onset of KH instability in free shear layers. That is progressively given way to convective instability when the laminar separation bubble contracts to the quasi-steady formation here. So I'd like to summarize the talk and open the floor for questions. First, a quick summary of the LSB topology and dynamics that are largely governed by the formation and evolution of shear layer roll-up vortices leading to laminar to turbulent transitions. And these structures arise due to rapid amplification of disturbances in the shear layer, leading to shear layer roll-up. What's important to note here is that linear stability analysis confirms that there is a continuous spectrum of characteristics of the flow instabilities spanning laminar boundary layer and separated shear layer, linking laminar boundary layer, LSB transition, to upstream flow development, as one would expect. The flow development in the aft portion of the bubble is highly three-dimensional, even on nominally two-dimensional geometries. It manifests in progressive deformation of shear layer vortices with subsequent vortex breakdown. And the initial deformations may be attributed to the growth of oblique waves if present in the flow, which are inherently amplified in the bubble. And as we mentioned, this inherent amplification would take place in presence of any minute three-dimensional perturbations to the main normal mode. On finite wings, open laminar separation bubbles form due to wingtip and wing root effects, and away from the affected regions, LSB topology and dynamics appear to be quasi-two-dimensional, with the shedding process and dynamics of the bubble locking onto a common frequency despite effective angle of attack variation across the span. And the LSB bursting as initiated in the mid-span region in the models, but generally we conjecture that this would be taking place where the locally laminar separation bubble has the thickest height and spans outwards from that region along the span, while the reverse progression is observed when LSB reforms. And overall, these transient last on the order of 10 convective time units that are shorter for the airfoil than on the finite wing. An LSB formation and airfoil starting from rest is notably different from reformation after bursting, and in this case, the onset of LSB formation is associated with an absolute instability, or it looks like an absolute instability as the flow develops, very similar to KH instability onset in free shear layers. And the transient process also lasts 5 to 10 convective time scales, which is an important consideration, of course, for experimentation and or numerical simulations where you need to wait for this long in order for flow to reach quasi-steady state. I'd like to, with this, acknowledge people who actually did most of the work, so my graduate students and co-PIs from TU Delft, as well as the University of Bundeswehr Munich, as well as funders of this work from federal and provincial government in Canada, Germany, as well as our industrial partners. With this, I'd like to thank you for your attention and open the floor for questions, please.
Thank you very much, Sahi, for the nice talk. It's a very comprehensive study for the past few years on the flow separation bubble. And I think it's really nice to see how these comparison between 2D and 3D, quasi 3D works goes. I think we can go for questions from the audience. Also, there will be questions from the live stream of Elsevier online. So you can just raise your hand and then I will unmute you. Maybe before the audience start, I actually have one question I want to discuss. Because I see when you have this, say, tip effect involved, the emergence of the separation bubble really goes in the very middle of the airfoil. Is this related to the aspect ratio of the airfoil at this moment?
Yes, thank you very much, Ching. Very insightful comment. So of course, when we open the question to three-dimensional geometries, it's proverbial can of worms, as we say in English. So obviously your parameter space changes quite dramatically. So here we would potentially have aspect ratio effects for certain planform, twist, and many other taper and height and other three-dimensional effects. So yes, absolutely, the location and span-wise variation of the bubble height are most likely to be dependent on the aspect ratio. and as well as other parameters. So there's no question about it. However, the important general trends, I think, are going to be observed in a similar fashion, and we've since performed experiments on different aspect ratios, and that's what we're seeing. So we doubled the aspect ratio just to be sure, and a very similar progression of the dynamics is observed.
Okay. And also when you have like this, say you turn down the tunnel and record actually the onset, like say the bursting part of the separation bubble, actually you see that it's kind of similar at the starting phase as what like in the past tail do in 2018, something like the sausage type of say bubbles. Is there any say difference comparing to that, and what would be the spanwise motion effect for the evolvement?
So we don't know, because we haven't actually, for the pure formation of the laminar separation bubble from rest, we haven't checked the spanwise flow development. So we only looked at the plane. There's no reason to believe that this would be very different than the quasi-steady state, but at this point I can only speculate about it. So we haven't looked into the spanwise flow.
Okay, okay, thank you. So questions from the audience? You can just raise your hand so I can unmute you. Yes. Yeah, I think you can speak.
Yes. Hello.
We can hear you.
Oh, okay. Professor Yosevich, from the slides number 31 to 32, I've noticed that there's a Reynolds number change, which means the free stream velocity change. It will obviously cause the hysteresis effect. So I wonder, is there any hysteresis effect happened in the experimental? And if it is, may I ask that what factor could possibly influence the hysteresis?
Okay, excellent question. And yes, for the members of the audience who may not be aware of this, with these types of flows, the flow history and memory plays an important role. So approaching the same state from two different directions will change the way the system behaves. And in this particular situation, of course, when you have separating flow without reattachment or separating flow with reattachment, you will observe the hysteresis effect. So that is, the flow will stall at different times depending on whether or not you're approaching it from decreasing flow velocity, and will reattach at a different Reynolds number when you're trying to go back. So if I were to show you the comparison of these results, you would see clearly the hysteresis, and you're absolutely right, it will play a role here. What we're doing here is we're making sure that the starting state and the end state are matched independent of the direction. So our starting state and an end state are outside of the hysteresis loops. That is, when we're starting at this Reynolds number and decreasing it to this Reynolds number, our mean lift characteristics here and here would match, right? Yeah. So the starting state and the end state, the quasi-steady states, are achieved equivalent characteristics for both flow development and the forces generated on the wing for these experimental conditions. However, when exactly this change happens, when the reattachment happens and when the stow happens, you can observe that this happens at a slightly different effective Reynolds number. And you're absolutely right. And this is the hysteresis effect. And sorry, your other part of the question, I believe, was what affects this hysteresis. And it is sensitive for a given geometry and of course, geometric characteristics of the model. It is sensitive to the rate of change of the parameter. So acceleration in this case, or deceleration, or in the case of the angle of attack change, the rate of change of the angle of attack. So with a very slow change, the hysteresis effect will be minor, and with a very fast change, it will be quite significant. And of course, this can be related to the fundamentals, because the stronger your acceleration, the stronger the artificially imposed pressure gradient will be in the flow.
Yeah, I got it. Thank you very much, Professor Yosovich.
Thank you.
Okay, any other questions? I see one. Yes.
Can you hear me?
Yes.
Oh, can you hear me?
Yeah, we can hear
we can
you.
Thank you for your awesome presentation. Can you turn to the 34th slide? Oh, 33, sorry. The bursting of separation start at the mid-plane. But I am curious about when the angle of attack is not zero, will it still start at the middle span? Because there will be difference between the suction and the pressure surface when the angle of attack is not zero.
Okay, yeah, so just to be clear, in this case, the angle of attack is not zero. So the angle of attack here is around 10 degrees, I believe.
And the tip vortex due to the angle of attack will not inflect the start location of the bursting of the separation bubble.
So that I understand, the question is how the bursting will progress if the angle of attack is aerodynamic zero. Is that correct?
Yeah.
Okay, so the results that are shown here for the audience are at a non-zero angle of attack, so it's a close to stall angle, around 10 degrees in this case. And if the angle of attack was close to the aerodynamic angle of attack zero, would the progression be similar? We've done results at the 5 degrees, and the progression is quite similar. So like the problem with zero angle of attack, you can't really have aerodynamic zero angle of attack in this dynamic system, because you always have a slight imbalance between the two sides of the wing, minor imperfections, etc. So on the average, it works out to be, but realistically, you will always have slight asymmetry between the two separated flow regions on the top and the bottom. The tip vortex region, or the tip effect region, will certainly be different, but in terms of bursting, we seem to see the same process at a lower angles of attack. Where the maximum height of the bubble will change, of course, slightly, because it depends on the three-dimensional characteristics of the flow, but it will start wherever the local maximum is in height.
Thank you.
Thank you for the question.
Actually, following this page, do you still see the tonal-like spectra when you have when this kind of bursting effect occurs?
In terms of how the shedding process responds, yeah, it's a continuous change between in the frequency, right? So when the Reynolds number increases, the frequency naturally increases, and it increases in a continuous manner. And when the Reynolds number decreases, the opposite happens.
Okay. I mean, it's like more a broad nature of the spectra in this case?
Yeah, so in this particular situation, there will be no tonal noise generated because the separated flow region is far enough upstream of the trailing edge. So the vortices are broken up by the time I can maybe allude to this.
Yeah.
So the vortices are broken up by the time they reach the trailing edge. So they're forming around this region, and they're fully incoherent in a spanwise direction by the time they reach the trailing edge. So it would be a broadband noise in their acoustic signature.
Okay. Okay. More questions from the audience? Let's. You can also leave the question in the chat and also type it. Okay, I think if there is no more questions, would like to thank Professor Jarusevic for the very nice and interesting talk. And also I see that there are like 3,000 likes on the Elsevier stream, because there are more people looking at the live stream than coming in this Teams room. So it's a very, very well received talk. And also, I forgot to mention in the very beginning that your Professor Jarusevic is also the host for the next experimental fluid mechanics conference. It will be in Canada, and there is also the deadline coming in December. In the say the December the 13th, I think. So it would be also very welcome that people submit papers and go. We meet Professor Jarusevic directly in Canada. Yeah, here is a link.
Thank you, Jing. Much appreciated. Thank you. I dropped in the link to the conference for anyone who is interested, and thank you very much for attending. It's been a pleasure to present some of our findings to you and answer insightful questions. So please don't hesitate to reach out if you have any questions or comments. I would be more than happy to engage in the email conversation, and hope to see many of you at the conference.
Yeah. Okay. Thank you very much, Sahi.
Thank you. Goodbye,
Bye.
everybody. Bye.
Thank you, Sahi. Bye bye.
Thank you.